Okay, let's work these two impulse examples. In the first example, we have a very tiny paint chip that embeds itself in the window of a space shuttle or something like that. And we're asked to calculate the average force on the window. Okay? And we can use our expression for impulse to do this. So we're interested in the average force. Okay? So we can rewrite this equation. And this is the average force on the paint chip. Divide both sides by delta t. It's mass of the paint chip times the change in velocity divided by delta t. And this will give us the average force on the paint chip. Okay? Now we're told the paint chip is moving towards the window, and we'll try to draw this here. Here's our window, and our little paint chip is initially moving at 4,000 meters per second, and it embeds itself in the window. Okay, so we can use this to calculate the average force on the paint chip then, based on the change in velocity of the paint chip and the time over which the impact occurs. So the mass of the paint chip is 0.1 milligrams. And we've got to get that into kilograms. So in 1 kilogram, there are 1,000 grams. And in 1 gram, there are 1,000 milligrams. So there are 1,000,000 milligrams in 1 kilogram. So 0.1 milligram is a tiny amount of mass. It's 0.1 times 10 to the minus 6 kilograms. Because remember, we have to have this all in the right units. So 0.1, let's try that again here, make that look a little better. 10 to the minus 6 kilograms. Okay? And what's the change in velocity? Well, we go from a speed of 4,000 meters per second to 0. So the change in velocity then is the final velocity minus initial velocity. The final velocity is 0. Initial velocity is 4,000 meters per second, so minus 4,000. So the change in velocity then is minus 4,000 meters per second. And that just barely fits. Okay? Divided by delta t. And we're told the time over which the collision occurs is 6 times 10 to the minus 8 seconds. Okay? So you do this calculation, do all that stuff there, and you find the average force is something incredibly huge. It's 6,670 newtons. Okay. Now, in terms of pounds, that's about 1,500 pounds. So the impact of this tiny, tiny paint chip, 0.1 milligram paint chip, into the window exerts 1,500 pounds of force, nearly a ton of force. And not only that, but it's concentrated on a very small area on the window. So it can do a tremendous amount of damage. So this is kind of a big hazard of space travel, is just this kind of leftover debris that's floating around out there. Since these things are all in orbit around the Earth, there's a chance that you can kind of, be going against the grain, so to speak, and kind of, and for orbits to cross one another. And when they do this, they're going at tremendous speeds. So such a collision is kind of a big concern in space missions. And incidentally, I forgot to, I kind of dropped the negative sign here. This really gives you a negative answer. And what that's telling you is the force on the paint chip is negative. We define the positive direction, okay, we gave 4,000 meters per second is the velocity of the paint chip. So we right away define the positive direction is into the window. Okay, so the minus direction is away from the window. This is saying that this is the force acting on the paint chip. Now, by Newton's third law, therefore the paint chip exerts that exact same force on the window, 6670 newtons. Okay, let's do the second impulse example here. And so I'm going to do some erasing here. Okay, in our second example, we have a bumper car. And we're told that in bringing a bumper car, the wall exerts on the bumper car 4,000 newtons of force over 0.2 seconds. Okay? And so we're asked to calculate the impulse, J. And so again, the impulse is the force exerted times the time over which that force is exerted. And this was 4,000 newtons. This was 0.2 seconds. So that gives the result for the impulse is 800 kilogram meters per second. So kind of an answer that doesn't mean a whole lot by itself, really. And it doesn't mean anything until we do part B of the problem. And in part B of the problem, we're told that the bumper car has 2.8 meters, but it's going at 2.8 meters per second into the wall, and we're asked to calculate the final velocity based on this. So so here's what we're given in part B. The velocity, the initial velocity of the car is 2.8 meters per second, and the mass of car plus driver is 200 kilograms. So let's look at this situation in a little more detail first before we just jump right in and plug stuff in here. So here's our wall, and our bumper car is coming into the wall, and in part A of the problem, we right away defined the positive direction. Okay? Our force was 4,000 newtons plus 4,000, and the force of the wall in the car is to the right. So in part A, we define the positive direction is away from the wall. Okay? Because we said, well, plus 4,000 newtons of force acts on the car. If we would have said it was negative 4,000 newtons, then that would have been the negative direction. This would have been the positive direction. But we said, well, that's the positive direction, because that's the direction the wall applies a force on the car. Okay? So therefore, what about our initial velocity of 2.8 meters per second? Well, if the car is moving into the wall, its initial velocity then is negative 2.8 meters per second. So this is negative then. Okay? That's just the convention we adopted from part A. Okay, so impulse equals mass times the change in velocity. So our impulse then equals mass times V final minus V initial. Okay, that's just our expression for impulse up here. J, as we calculated up here, was 800. The mass of the car, 200. And our initial velocity, again, is minus 2.8. So V final minus negative 2.8 gives you V final plus 2.8 meters per second. So you solve this, divide both sides by 200. 800 divided by 200 gives you 4 here. And when you solve for V final, you get the answer plus positive 1.2 meters per second. So everything worked out nicely then. We had a negative velocity coming into the wall. Our final velocity is positive, meaning it's away from the wall.